Hello students, welcome to our second theory session of carbon and its compounds. In our previous session, I discussed about the position of carbon in the periodic table, its atomic number, its atomic weight, and the type of bonds it is forming. About the valency of carbon, I told you that carbon is tetravalent because it has got 4 electrons in the valence shell. Now in this session, we will be discussing about the allotropes. Now let's take up the allotropes. Now here children, what are allotropes? Do you have any idea what are allotropes? Allotropes are what? Different forms of an element having different physical properties but similar chemical properties are called allotropes. Now what do you mean by physical properties? Children, physical property means the state, right? First of all, its state, whether it is in compact solid state or it is in amorphous form or it is in gaseous form. Allotropes will discuss about the crystalline form or the amorphous form. Or its physical properties like boiling point, like melting point. These are all what children? Density. These are the physical properties. And the chemical properties, that is the particular reactions, what it is giving with acids or bases or water or oxygen or any other chemical compound. So what are allotropes? They have what? What is to be remembered here is children, it is that they have a different physical property, right? You should remember this because it can be asked in your objective type questions. And they have what? They have your similar chemical properties. So what are these compounds called? These are called as allotrope. Okay. Now this phenomenon is called as what? Allotropy. Now our carbon shows allotropy. That is, it exists in different forms. So it exists in different forms with a different physical property but a similar chemical property. Is my point clear? Now, what are the allotropic forms of carbon, children? They are diamond, graphite, and one is Buckminster Fullerene. This is one of the allotropic form of carbon. Now, these diamond and graphite are the two crystalline allotropes of carbon. Now, if I say, children, there are large number of allotropic forms of carbon, like coal, like coke. All are these what? These are also the allotropic forms of carbon. Now, one of the allotrope is what, children? This is Buckminster Fullerene. Diamonds and graphite are the two crystalline allotropes of carbon. Now, these diamond and graphite, they both form what type of crystals? They form covalent crystals. I have told you that carbon is not at all forming ionic bond. I'll tell you one compound where it is forming ionic bond. It is aluminium carbide, that is Al2C3. Their carbon is existing in its ionic form, right? That is C4- form. And that reaction, that formation of aluminium carbide takes place at very, very high temperatures, some 900 or 1000 degrees centigrade. Silicon carbide, that is a covalent compound. So the only ionic compound is aluminium carbides. Rather, carbides are the ionic compounds. So they are very, very stable. Rest all compounds are what, children? Covalent. Now let's take up the allotropes. The three allotropic forms of carbon. I have told you, diamond, graphite and Buckminster Fullerene. And diamonds and graphites are the two crystalline allotropes and these are covalent crystals. Now this is your diamond. You all must have seen diamond, how sparkling shine it has. It is a covalent crystal. It scatters light. Now let's see why it has got this tough structure. It is the hardest material on earth, right? And it is also used as a glass cutter, and it has this shining surface. Let's study about its structure. Now children, each carbon atom in diamond is linked to 4 other carbon atoms by strong covalent bonds, right? Like here, one carbon atom, this one is linked to what all? This particular carbon atom, right? This is linked to 4 other carbon atoms, 1, 2, 3 and 4. And what type of bonds are present here? They are the strong covalent bonds. The 4 surrounding carbon atoms are at the 4 vertices of a regular tetrahedron. Now here children, if I am joining these lines, what I'll get? I'll get a regular tetrahedron here. Say if I am joining this to this, I am joining this C2 to C3. Again I am joining this C3 to C4 and you're the C1 to C4. Right? So what am I getting here? I am getting a tetrahedron. So these carbon atoms are present at the vertices of the tetrahedron. Now what does this lead to? This leads to a 3-dimensional network of covalent bonds. Every carbon atom in diamond children is linked to 4 other carbons by a covalent bond. Now due to this covalent bond or this 3-dimensional network, diamond has got what? It has a rigid structure. It is a very strong compound, right? Or it is a very strong allotrope of carbon. Now to see the covalent structure of diamond, see this is the covalent carbon. This carbon and this is again linked to the 4 other carbons. You take up any carbon from here. These are what? These are carbon atoms and these are the covalent bonds. Take up any carbon. Say this carbon, it is linked to 1, 2, 3 and 4th carbon. So every carbon is linked to 4 other carbon atoms. And this leads to a very strong 3-dimensional structure. Right? Now this diamond children, it is a non-conductor of electricity. So diamond doesn't conduct electricity. Why? Because each carbon is joined to 4 other carbon atoms. This I have told you. Now carbon has 4 electrons in its valence shell. So only how many electrons are there? 4. And each carbon in diamond is bonded to 4 other carbon atoms by covalent bonds. Like, say if I am taking a carbon here, this carbon has what? How many electrons children? This carbon has 4 electrons. 1, 2, 3 and 4. Now this carbon is again bonded to how many electrons? To how many carbon atoms here? It is 4. Right? So there are 4 more carbon atoms bonded to it. And 4. Right? So as a result of which what happens? There are no free electrons in the diamond crystal. All the valence electrons are occupied. So what is left here is there are no free electrons in the diamond crystal. So due to the absence of free electrons, diamond is a non-conductor of electricity. As there is no free electrons, so diamond doesn't conduct electricity. It scatters light. It has a very high melting point, right? But it is a non-conductor of electricity. Now let's take up its another allotrope, that is graphite. Now in graphite children, what happens? I told you that what are the allotropes? In allotropes, the physical properties are different, but the chemical properties remain the same. It will burn diamond at a very high temperature. The product you will get is carbon dioxide. If you'll burn graphite, the product you'll get is carbon dioxide. Even if you'll burn coke or coal or lump black or Buckminster Fullerene, the only product you're getting is carbon dioxide, right? So, what is the difference here? The difference is the state in which they are present and their melting points, their densities, their boiling points, as well as their state, right? Now in this graphite is used in your pencil leads. You must have seen it is soft and slippery. Why? This is again due to the difference in arrangement of the carbon atoms. Now the carbon atoms are arranged in flat parallel layers as regular hexagons. These are arranged in layers. And how was that in your diamond? It was a three-dimensional network. Okay. Now each carbon in these layers is bonded to three other carbon atoms by covalent bonds. Now remember children, in graphite, each carbon was bonded to how many carbon atoms? 4. But in graphite, each carbon is bonded to how many carbon atoms? 3. Right? Now there is a weak van der Waals force of attraction between adjacent layers. What are we saying? That different layers are present. Right? Now in between the layers there has to be some force. If there is no force, these layers will fly off. So this weak van der Waals forces of attraction is present. I'll tell you what is this force. Layers of graphite can slide over one another. They can just move over one another. Right? Due to sheet-like structure, graphite is a soft substance. Now these layers can slide over one another. What are these van der Waals forces of attraction? Children, this is a very weak force. And this is a force of attraction between nucleus of one atom and electrons of the other atom. Is my point clear? Van der Waals force of attraction is a weak force. That is, it is a force of attraction between nucleus of one atom and electrons of the other atom. Now let's see how these layers are present, children. Yeah, these are the hexagonal layers which are present. This is the first layer, the second layer and the third layer. And in between these layers, what type of force is there? Van der Waals force of attraction. In between these two layers is again a van der Waals force of attraction. Now here children, what is happening? Each carbon is bonded to three other carbon atoms. That is, this is bonded to 1, 2 and 3. 1 at the bottom. Okay, here again these carbon is bonded to 1, 2 and 3. But I told you, how many electrons are present in the valence shell? 4. So what about that one electron? That one electron is not bonded. So it will move in between these shells. Right? Now let's see why this graphite. By this we can conclude that graphite is a soft structure. It is very soft substance. Why? Because these layers, that is layer 1, layer 2, layer 3 and layer 4, layer 5. So many layers can be present. So these layers can slide over one another. So because of the sliding, because it doesn't have the tough structure, it is soft. Right? Now let's see, it's one more important property, that is graphite is a good conductor of electricity. I have told you this. Each carbon atom is bonded to only 3 carbon atoms. Right? By what type of bonds? By covalent bonds. Now the 4th valence electron of each carbon atom is free to move. Right? That electron is moving between the shells. Now due to the presence of free electron, graphite is a good conductor of electricity. Now here what is your carbon doing is, I'll just draw its structure. Say, this is your carbon, children. This is a carbon, right? Now here this one electron is free, whereas it is bonded to how many other carbon atoms? It is bonded to 3 other carbon atoms. That is 1, 2 and 3. Now this particular electron is free. Now what this electron will do? This electron can move from one shell to the another shell, and that is why your graphite is a good conductor of electricity. Diamond was not a good conductor of electricity because there all the 4 electrons were occupied. Okay, so this is one of the important allotrope of graphite. Now let's take up its another allotrope, that is fullerene. What is this fullerene? C32, that is 32 carbon atoms bonded together. C50 is again 50 carbon atoms. C60, C70, C76, C84. These are all what? These are the allotropes of carbon, and these are called fullerene. Right? So say in one fullerene there are 70 carbon atoms which are bonded by covalent bonds. Each carbon can be either bonded to 4 other carbon atoms or to 3 carbon atoms. Right? So it's a mix of both the two. The carbon atom can be bonded to 4 or can be bonded to 3. The most commonly known fullerene is C60. Now this C60, children, is a mustard colored solid at room temperature. You must be remembering fullerene is a amorphous allotrope. It is not a crystalline allotrope. Your diamond and graphite are the crystalline allotropes, whereas this fullerene is an amorphous allotrope. Now this C60. C60 was named Buckminster Fullerene. Why? Why they are giving this name to it? After American architect, he was an architect on whom the C60 was named. It was Buckminster Fuller. Why? Because its structure resembled the framework of dome-shaped hall designed by Fuller. So Fuller designed a dome-shaped wall, and the structure of that wall resembles your structure of C60. So that is why C60 is called as what? Buckminster Fullerene. Let's take up its structure. Now how we can conclude that this is formed of carbon only? I have got a soccer ball like structure in my hand, or I have got a ball. How can I say that this is formed of carbon only? How can I be sure of that there are no other elements present in it? By burning it. Remember this one thing clearly, that once you burn a substance, the gases formed as well as the residues left will tell you what that substance is composed of. So when Buckminster Fullerene is burnt, what is formed is only carbon dioxide is formed when Buckminster Fullerene is burnt in oxygen, right? And no residues are left. So, is there any residues left when Buckminster Fullerene is burnt? No. Only what is the thing formed is carbon dioxide. That's it. Now this suggests that it is made up of carbon only, right? Like your graphite. If you burn graphite, you'll get only carbon dioxide. Nothing you'll get. So it is again an allotrope of carbon. Now this is, I told you, it is an amorphous allotrope of fullerene. I am telling you repeatedly whether it's amorphous or crystalline. Do remember these things in mind. It is an amorphous allotrope of fullerene. It is neither hard like diamond nor soft like graphite. Got it? So it is neither hard nor soft. So this is your Buckminster Fullerene. Now let's see how these carbon atoms are arranged so that it is giving a different structure. Yeah, it is a football-shaped spherical molecule in which 60 carbon atoms are arranged in interlocking hexagonal and pentagonal rings of carbon atoms. So in your diamond, carbons were arranged tetrahedrally. In graphite, carbons were arranged in hexagonal rings. Whereas in fullerene, you have got both the types of rings. What are these rings? The hexagonal ring as well as the pentagonal ring. Is my point clear? So, how many hexagons are it is made up of? It is made up of 20 hexagons. Your C60, right, is made up of 20 hexagons and 12 pentagons, right, with a pattern called the truncated icosahedron. So this is a pattern. That's it. You don't have to rush into the dictionary or find out the meaning of it. That is not required. Truncated icosahedron. It is a pattern in which hexagons and pentagons are arranged. Okay. Now in this truncated icosahedron, what happens? The pentagons are kept far apart from the hexagons. So what happens, children? In your truncated icosahedron, the pentagons are far apart from the hexagons. That's it. Now let's see how it looks, how it appears. It appears like this. This is the molecular structure of fullerene, children. Otherwise it resembles a soccer ball. But this is a molecular structure. See, this is a pentagon, I think. 1, 2, 3, 4, 5, 6. This is a hexagon. Right? So if here is a hexagon, where will be pentagon? It will be somewhere outside. So it is folded so that the pentagons are placed far apart from the hexagons. So there are hexagons and the pentagons. So this is the molecular structure of your C60 molecule or Buckminster fullerene. And let's take up its properties. The structure bends around and closes to form a soccer ball shaped molecule. You saw that, right? I hope you saw that. The structure has bended around. Now what type of structure it is taking up? It is taking up a soccer ball shaped molecule. And it is also called as what? Buckyball. Right? Now you remember, children, it is a carbon compound and it is soluble in toluene, in benzene and other hydrocarbon solvents. What I told you was how it appears. It is a mustard colored solid. But after dissolving in toluene or benzene, especially in benzene, if I am dissolving fullerene in benzene, it gives a magenta color. Right? So it is soluble in your toluene, benzene and other hydrocarbon. Now it polymerizes on exposure to UV radiations. Just tell me what you mean by polymerization. Polymerization is that this C60 will be linked to more molecules and it will form a polymer. Polymer consists of large number of monomers. Say one monomer is C60. The another monomer would be again C60. Another monomer C60. Say polymer. So when it is more than 4 monomers, it becomes a polymer. So when you expose this Buckminster fullerene to UV light, what will happen? It will get polymerized. Right? Now let's see finally how this looks like a soccer ball. This looks like this ball, children. This is a soccer ball and fullerene looks like this. Now fullerene is a very good lubricant, excellent lubricant. Why? Because you see it's a ball-like structure. So it slides. It's not like your grease or any other lubricant oil. Here the molecules are in the form of ball. So the ball moves off. But the only drawback with this fullerene is that you cannot take it to high temperatures. The moment it goes to high temperatures, it decomposes, right? Or it reacts with other substances. So though it has got a good lubricant property, but its use is still restricted. We cannot use fullerene as a lubricant. It has lots of other commercial uses also. So this is your soccer ball, and your soccer ball gives the fullerene is like this soccer ball. Okay, so these are some of the allotropes of carbon which you have to study. Your coal is an amorphous allotrope. It's just the carbon atoms which are loosely bonded to each other. Right? We will be dealing with organic compounds in our next session. So I'm concluding for this session, and I hope you understood the structures of diamond, graphite and fullerene, and also why diamond is a non-conductor of electricity and heat, whereas graphite is a good conductor of electricity. Right? Why fullerene is a lubricant. So these are very small points, children. You have to remember these. This is a very important topic. You get lots of questions from this in your Olympiads also, and when you'll fight for your engineering or medical entrance, there also you'll get questions from this. So I'll conclude this lecture, and thank you very much, children, for listening patiently. In the next lecture, I'll discuss the hydrocarbons, the aliphatic compounds, the aromatic compounds and their nomenclature.